Functions are increasing in intervals where first derivative is positive. Functions are decreasing in intervals where the first derivative is negative. To locate these intervals, mark the critical numbers of your function on a number line and test numbers around them in the first derivative to see if your rate of change is positive or negative. So this is a continuation of the video before. Let's take the function negative 3x squared plus 12x. Excuse me. Its first derivative is negative 6x plus 12. Hilltops and valley floors occur where your first derivative is 0. There's no rate of change at a hilltop or a valley floor. Add 6x to both sides, divide by 6, and you get a critical number of 2. So over here on the graph, again, this is just a courtesy. This is the graph of our original function. 2 is the location of a hilltop in this case. Our first derivative, negative 6x plus 12, is what we're going to use to test the rates of change. So below here to your bottom right, 2 is our critical number, and I'm going to test a number smaller than 2 and a number larger than 2. When we plug 1 into the first derivative, we get an answer of 6, which is positive. That just tells us our function is increasing left of the critical number. The test number to the right of the critical number, we chose 3, gives us a negative answer, and that tells us that a negative rate of change means our function decreases on the right side of the critical number. As far as interval goes, if you look at the top right of your screen, our function increases from negative infinity to 2, and then it decreases from 2 to infinity. As far as writing your intervals go, you're just writing down the values of x for which the function is increasing, and that was negative infinity to 2, decrease 2 to infinity. Your critical number will be the cutoff number in your interval. Let's take the function negative x cubed plus 12x, and its graph is over here to the right. Our first derivative is negative 3x squared plus 12. We want to know where those rates of change are 0, because those will be valley floors and hilltops. These two terms have a 3 in common, but I'm going to go ahead and pull a negative 3 out of here. First term divided by negative 3 is x squared. Second term divided by negative 3 is negative 4. You can always redistribute to check your math. Our factoring is good so far. This is a difference of 2 perfect squares, so x squared breaks down to x and x. Square root of 4 is 2, and because there's no middle term, we put in a plus and a minus. If you were to FOIL these two, you would get x squared minus 4. Negative 3 does not contain a variable. X plus 2 is 0 when x is negative 2. X minus 2 is equal to 0 when x is positive 2. So our critical numbers, negative 2 and positive 2, mark hilltops and valley floors. We're going to put both of those numbers on a number line. Negative 2 and positive 2. We're going to test in and around those critical numbers. Sorry, y'all. Left of the first critical number, we picked a test number of negative 4 in class. Between the critical numbers, we picked 1. You could also use 0. 0 is easy if that's a possibility. And then a number right of the second critical number, we need to test all 3 of these intervals. Left of the first critical number, we chose negative 4. In our first derivative, we sub in negative 4, and our answer was negative 36. So our graph is decreasing in that interval. A test number between the criticals, we picked 1. You could also pick 0. 1 plugged into our first derivative gave us a result of positive 9. Our graph increases between the critical numbers. And then finally, when you test right of the second critical number, we picked 4 in class. So our first derivative with a 4 subbed in gave us a negative 36. Negative means decreasing. And so we have two sections, two intervals where our graph is decreasing and only one of increasing. So below, let's look at the graph first. Notice that in purple, we have two intervals of decreasing. That interval and that interval. That matches our mathematics below. We only had one interval of increasing, and that was between the criticals, and that matches our mathematics there. So writing these intervals, we only had increasing between the criticals, between -2 and 2. We had decreasing before the first critical and after the second critical. -infinity to -2 is this part, or 2 to +infinity is this part. For the function x squared plus 8x plus 16, the graph over here to the left, we take our first derivative, which is 2x plus 8. That is equal to 0 when x is -4. That's only one critical number, which coincides with the graph of our function. Our function is the shape of a parabola, specifically a valley. Visually, we can see our graph decreases until we get to the critical number and then increases afterwards. Let's see if the mathematics will back that up. -4 was our critical number, so we mark that on a number line, pick a number smaller and larger, test them in the first derivative. In class, we picked -8 and 0. -8 plugged into our first derivative gave us a negative answer. So we decrease before we get to the first critical number, well, the only critical number. And then we tested 0 for the interval to the right of the critical number. We got a positive answer, so our graph increases. We decrease to the first critical, to the critical number, and then we increase afterwards. That coincides with our graph. Decreasing, critical number, increasing. Same thing down here. The interval of increasing is to the right of the critical number, so we pick -4 to +infinity for increasing, -4 to infinity. The decreasing was -infinity up until we got to the critical number, -infinity to -4. And then something extra you'll be asked in your homework is relative minimum and or relative maximum. That is the actual point at the top of the hill or the valley. So far, we've used critical numbers just to identify the x-coordinate. This is the first time we've done the y-coordinate as well. And what you do is you go to the original function and you substitute in your critical number. Our graph pertains to the original function. So if we put -4 into the original function and calculate, we'll actually get 0 as our answer. So that tells us this is a relative minimum at the point -4, and your x-coordinate will always match your critical number. The y-coordinate will come from the original function once you've substituted the critical number into it. So that's called a relative extrema. It's a local minimum for our problem. And I'm going to scroll back down. This is where we did the math. The original function, notice there's no apostrophe representing derivative. So f of -4 plugged into our original function gave us an answer of 0. And any point on the graph is a combination of the number you plug in and the answer you get. Okay. Let's do another example. Let's take a function defined as -3x squared plus 2x plus 7. Its graph is over here to the right. There's only one hilltop, so we expect only one critical number. Taking our first derivative, we get -6x plus 2. That is equal to 0 when x is 1/3. A critical number of 1/3 just tells us that when x is 1/3, we're, in this case, at a hilltop. So we're going to test on either side of the critical number. So 1/3 is marked. Left of the critical number, we picked 0. Right, we picked 1. You can pick any number smaller than 1/3 and any number larger than 1/3 as your test numbers. Those are totally fine. Pick numbers that are friendly. So in our first derivative, we have negative 6x plus 2. So using 0 as a test number, negative 6 times 0 plus 2 is positive. That tells us our function increases to the left of the critical number. Our test number of 1 subbed into the derivative gives us negative 4. And so we're decreasing to the right of the critical number. So increasing is negative infinity until you hit the critical number, negative infinity to 1/3. Decreasing is 1/3 to infinity, the right side of the critical number. The critical number is the cutoff for increasing and decreasing intervals. Now, when it comes to relative extrema, because this function goes from increasing to decreasing, we have a relative maximum or a hilltop. In the original function, you put your critical number of 1/3. 1/3 subbed into the original function gave us an answer of 22/3, which is a little more than 7. Pairing up the number you plugged in and the answer you got, you'll get 1/3 and 22/3. Let's go back to the top, and sure enough, the top of our hill has an x value of 1/3, the critical number, and a y coordinate of 22/3. That's the original function's value with the critical number subbed in. So this point, input and output, represents the top of the hill. I hope this video has helped out. If you have any questions, reach out by email, call my office, or ask in class if we're meeting in a traditional setting. Thank you.